Okay, AP Physics 2, Unit 3, Lesson A, multiple choice, the third of 4 videos for Lesson A's multiple choice. There's a lot of them. It's an important unit. Let's get started. 41 to 47, and then 49 to 51. 4 objects, each with charge Q, are held in a fixed square with the sides length D is shown in the figure above. Objects X and Y are at the midpoints of the sides of the square. X and Y, X and Z. The electrostatic force exerted by object W on object X is equal to F. What is the magnitude of the net force exerted on object X by objects W, Y, and Z? Okay. So, they all have the same charge, and it's all positive. So the force on X is going to look like this. The force from W is going to be repulsive this way, and they already told us is F. And so the force by Y is going to be the same thing, but the opposite direction. Also F. The force by Z is going to be repulsive upward. It's going to be less than F. Because this distance is larger. Let me change that to blue. Because this distance is larger than the distance, it's double the distance, as a matter of fact. So, if it's double the distance, that goes in the bottom and gets squared. So that's going to be a fourth of F. And since the W and Y cancel out, all there is Z. So I would go with A in this case. Yeah, double the distance, cut the force down to a quarter of what it was. The figure shows 2 particles, each with charge positive Q, that are located on opposite corners of a square of side D. What is the direction of the net electric field at point P? So now we're looking at field. So we'll go blue here and red here. Now the field by the red is going to be downward, we'll say that much. The field by Q on the right, the blue one, is going to be the same size because it's the same distance away, but to the left, and the reason why is because the field points in the direction that a positive test charge would go. So if you brought a little positive charge here and put it at P, it would be pushed to the left by the blue and be repelled downward by the red charge. The end result is going to be this. Add them as vectors. It's going to be down and to the left. So I would go with C in this case. Figure above shows the locations and charges of 3 objects. The magnitudes of the electric force exerted on the object located at the origin is most nearly. So they want the force on this guy. So let's go with this one is green and this one is blue. Let's see, well, really, let's go with the direction of the forces first. So they're close to this. This one's a little more charge, but it is farther away. So the 2 forces are going to be close to the same. Let's say the blue force is negative, so it's going to attract this positive charge this way by some force. And the green one is repulsive. And it's going to be pushing this way. Roughly the same, we'll figure out exactly. The end result is going to be this. So what we need to do is find the magnitude of the blue force, the magnitude of the green, and then add them using Pythagorean's theorem. So combine them as vectors. So we're going to find the green force, the green force squared plus the blue force squared and then take the square root, and that will be the magnitude we're looking for. All right, so let's go with the blue one first. Blue force is going to be K, 2 microcoulombs, well, okay, 2 times 10 to the negative 6 coulombs, times 5 times 10 to the negative 6. I'm not worried about the negative sign because I already know the directions. Divided by 0.3 meters squared. And then the green force is going to be K, 2 times 10 to the negative 6th, times 4 times 10 to the negative 6th, divided by 0.2 squared. Get both of those numbers, square each, add them together, and take the square root, and you'll get your answer. Now, the answer in this case comes out to be C. I am not going to spend my time pushing buttons on a calculator for you. Resolve this, resolve that, get two numbers, square them, add them together. If you should come up with something close to 2.1. We could do a quick thumbnail of it. You could do 2, so negative 6 times positive 6, that's going to cancel out. That's negative 9th, though. That's going to be 2 times 5. Is that 5? Divided by 0.3 squared. So it's going to be, it claims the answer is going to be C, so I'm willing to believe it. We are going to add them together. So run through. If you're struggling with the math part of it, just see me in class one day after school class or something, and we'll work it out. But this is how you're going to get it done. Figure above shows 3 objects, x, y, and z, that have charges negative 4q, q, and negative q, respectively. The objects are held fixed on an axis of position shown. The magnitude of the electrostatic force exerted by object y on z is F. What is the magnitude of the net electrostatic force exerted on y due to the other 2 objects? So if I'm y, we'll call z over here the green charge, and x will be the red one. So the force by the red one is going to be attractive. Well, let's do the green first. Green is going to be attractive this way, and it's going to be, say, this big. The red force is going to be 4 times larger because the charge is 4 associated with it is going to be larger. So it's going to be like out here. So it's going to be the force by x minus the force by z. But if z is, they call that F, this is going to be 4F, because the distance is the same, just the charges are increased. So I would expect 3F to be my answer. All right, this is 4F minus F, 3F. A metal sphere with a small negative charge hangs vertically from a light thread is shown in the figure above. The metal sphere is then brought near but does not touch an uncharged plastic sphere. Uncharged plastic sphere. Of the same size that is also hanging vertically on a light thread. Which of the line best shows how the spheres shows the 2 spheres after they've reached equilibrium? Alright. So the plastic sphere can only be polarized. So I'm looking for a situation. It's like bringing if I haven't done this demonstration, it's like bringing the charged balloon after you rub it on a sweater or your hair near a door. It will stick because the door, even though it's an insulator, will become polarized. This is their example of polarization here. So one of these 2 is my answer. And they are going to attract each other, because the negatives on the sphere are going to push the negatives as far away as they can get, which isn't super far, but it will turn the positive end of the molecules towards the things, and they will attract, just like the balloon stuck to the door. It's the exact replica of that demonstration. If I haven't done a balloon sticking to a door, then track me down in class and yell at me. In a friendly way, but yell at me. 46. 3-point charges, Q, little q, and big negative Q, are fixed at the corners of an isosceles triangle. Oh boy, we're getting all geometric. In the plane of the page shown above, which arrow in the figure represents the direction of the net electrostatic force on positive, a little positive Q, due to the other two equal and opposite charges? Okay, so call this red, call this green. The red one is going to repel, so it's going to push that whole thing this way. The green is going to attract, so it's going to pull it this way with the same force. And since they're the same, and we add them as vectors, I'm going to go with D as my answer. It's going to go to the right. .47. Oh boy. Represents two charged concentric conducting shells. So this one's charged and this one's charged. With radii R1 and R2. Space between the shells is filled with air. The dashed lines represent equal potentials. You know what? We're going to wait on this one. Because lines of equal potential we don't cover until lesson B. So we're going to wait. We're going to move that one to B. An initially uncharged electroscope consists of two thin, 50 centimeter long conducting wires attached to a cap. So I'm assuming it's metal, with a 25 gram conducting sphere attached to the other end of each wire. When a charged rod is brought close to but not touching the cap, the sphere separates. This is what they call a, no, I can't remember the name of it. An electroscope. Alright. This is tricky. I could figure out, using physics, I could figure out the magnitude, angles, and tensions, and I know the weight of the spheres and the length of the string. I could probably find out how strong the force is that each one is feeling. But the problem is, I have no way of knowing whether they're positive or negative. Because if I bring a positive rod here, then these will be positively charged and repel each other. If I bring a negatively charged, then negatives will fly away and go to here, and they'll be negatively charged. And they'll behave the same way. So there's no way to know the sign of the charges, but I could probably figure out the magnitude. So for 49, we're going to go with A. I'm glad they don't make me find the magnitude, because I get angles and components of this force, the y component be equal to the weight, and blah, blah, blah. So, sorry, this force here, the tension and all that. So, yeah, there'd be, be some work to do, but you could do it. Diagram shows the electric field lines in an isolated region of space containing two small charged spheres. Which of the following statements is true? Alright, so electric field lines go from positives and into negatives. So I can tell you right away, Y is positive, Z is negative. Now, do they have the same number of lines? Well, let's go through the answers. The charge on Y is negative and Z is positive. No, it's the other way around. So no. The strength of the electric field is the same everywhere. No. It's stronger where the lines are close. It's weaker where the lines are far away. So it's not the same everywhere. No. The electric field is strongest midway between Y and Z. Actually, I see it as being strongest really close to Z or really close to Y right here. The lines are even closer together. So I'd say no. A small negatively charged object placed at X would tend to move to the right. Placed at point X. Okay, so if I'm a little negative one, yes, because I'm going to be repelled by Z, which we've already determined must be negative. And that's going to be a stronger repulsion than the attraction by Y, because Y is farther away. And they don't carry the same sign. They're definitely opposite. So it's got to be D. Alright, 51. Two electrically neutral conducting rods are brought near a negatively charged sphere, as shown in the figure above. Rod 1 is touched to rod 2 for several seconds. So when that happens, they're going to act as one rod. So while they're in contact with each other, negatives are going to pile up on rod 2, positives are going to pile up on rod 1. Then they separate them, so that means rod 1 is now positively charged and rod 2 is negatively charged. The rods are then both removed from the vicinity of the charged sphere, which is how best describes the resulting net charge in each rod. So rod 1 is going to be positively charged, and rod 2 is negatively charged. A is our right answer.